In this lesson, we shall focus on MAT2615 Calculus in higher dimensions, also called Multivariable Calculus. We shall actually have an overview of the kinds of things that you need to know from the beginning to the end, the A to Z aspects of this module are the things and aspects we shall discuss today, and we're getting started. Right, first things first, we shall look at question 1. Let L be the line in R3 that passes through the points 1, -1, and -2, and 2, -1, and 1. Let V1 be the plane defined by this. So we have actually a plane whose equation has been given to us. And the first question says, find an equation for L. Right, so we need to find an equation for the line. Now, obviously, okay, obviously what you need to look at here,
Why?
we have been told that L is the line in R that passes through the points. So you have 2 points there, and therefore what we need to note is the following. Right, so given 2 points on the line, we need to know that a vector. Right, so we know that a vector, okay, right, a vector that is parallel to the line is given by, okay, a vector that is parallel to the line is given by, right. So at this point then, we note therefore that the vector is now, if you have this point and that, we can then say 2, -1, 1, -1, -2. Okay, so we subtract this. So moving from this initial point to the final point, we subtract them in this manner. So we take 2 -1, 1, and we subtract 1 -1 -2, and therefore the result is as follows. So we have like 2 -1, which is a 1, and then we have -1 plus 1, which gives us a 0, and then we have 1 plus 2, which gives us a 3. Okay, so a vector that is parallel to the line is given by this. Right, and because of this, then we then say thus. Right, that's the equation. That's the equation for L is given by X, Y, Z. Right, so obviously, like we said last time, we can take any of these 2 points, either this or that. The line passes through these points, or it passes through -1 or 1 -1 -2, right? So plus t times the vector 103, and t itself is an element of the real numbers. Okay, so this is the answer, because it said find the equation for L. Thus, the equation for L is given by that. So this answer to the first question, to the question A, is the one that we've written here. So think about it, and please advise if there's a question or there's something you would like us to add or remove from this. There, you have your turn. Right, Naledi. Any idea or anything we need to remove, add, or any changes you'd like us to make? Or any question?
I'm still copying the answer on my book.
Okay, that's fine. But also note that this is recorded, so I'll send you the video. So you'll have the video of this lesson, you know, after this, and you can watch anytime. So yeah, That's something that you can note. So, right, you done copying? Let me know, please. Right? Yes, no? Yes. Okay.
I'm still busy.
Okay, that's fine. All right, thanks. So let me know, please, when you're done copying. All right, let me know, please, when you're done copying. This discussion is an overview of the whole module. So today's discussion is like everything you need to know about the module. And then there are discussions we can have, which will be like on specific sections as well, in-depth discussions of specific sections. So now we note that obviously this is what we have. This is what we have. So a vector that is parallel to the line is given by this, because it's a line that passes through the points. And therefore, if you have a line passing through the points, then you have that a vector that is parallel to the line is given by the difference. Okay, also, I mean, here, you can actually take this minus that, or this minus that. So the order does not matter, or of subtraction of the two vectors, because both vectors, this and that, are vectors on the line L. Okay, and also simultaneously, we said that also this equation of the line is defined as the vector x, y, z, arbitrary vector, equals the a point through which the line passes. So it can be 1 minus 1 minus 2, or here we can put 2 minus 1 1. You know, we can actually do that. Okay, please let me know when you're done. Okay, so
I'm done.
okay, thank you so much. Let's move to the next question. Right, the next we're going to look at part B. Find an equation for the plane V2 that contains the line L and is perpendicular to V1. Right, so a couple of things therefore remain very important to say. How do we then find an equation for the plane V2 that contains the line L and is perpendicular to V1? So let's start. This is how we're going to present a solution to this. So we note that a normal, right, a normal vector, right, so we note that a normal vector perpendicular to the plane V1 is 1 1 minus 3. So we're saying a normal vector perpendicular to the plane V1. So I mean, we have V1 as a plane, whose equation is this. So the coefficients here are 1 1 minus 3. So and these coefficients constitute what you call a normal to the plane. So a normal vector perpendicular to the plane V1, here is a plane, and you have a normal, right? And this normal that is perpendicular to the plane is a normal that is indeed on the plane, but obviously perpendicular to the plane, like so. And it is the vector 1 1 minus 3. Just the coefficient of x is 1, that of y is 1. The coefficient of z is a minus 3. Okay, right, so full stop. And we shall continue to say since V2 is perpendicular, since V2 is perpendicular to V1, the vector 1 1 minus 3 is parallel to V2, and V2 contains the line L. Therefore, the vector, the vector 103 is also parallel to V2. The vector right. Okay, let's say here, then a vector perpendicular to V2 is. Okay, let us analyze this together. So we're saying that a normal vector perpendicular to the plane V1 is this. So obviously V1 has this plane. So let V1 be the plane defined by this. So V1 is a plane defined by this. But the normal to the plane V1, or a normal to this, is 1, 1 minus 3. Since V2 is perpendicular to V1, because here they said find an equation for the plane V2 that contains the line L and is perpendicular to V1. So we are noting that the plane V2 is perpendicular to V1. So in other words, if you have the two planes, you have the plane V2 and then you have the plane V1. So these two planes are perpendicular to each other. But we are saying find an equation for the plane V2 that contains the line L. So we notice that the line L is the line that is actually on the plane V2 and is perpendicular to V1. Okay, good. This is what we have. So we note therefore here that a normal vector perpendicular to the plane V1 is 1, 1 minus 3. Since V2 is perpendicular to V1, here's V2 perpendicular to V1, the vector 1, 1 minus 3 is parallel to V2. Okay, this is good news because we're able to see that to V2 there is a normal, and the normal is the vector 1, 1 minus 3. Okay, so there is a vector 1, 1 minus 3. It is always given a plane. If this is the equation of the plane, then the vector formed by the coefficient of x, of y, of z, these coefficients constitute what you call a normal vector perpendicular to the plane. So yeah, right. So it's perpendicular to V1. Note that it is perpendicular to V1. So let V1 be the plane defined by this. So in other words, you can get a normal to it. So perpendicular to V1 is the vector 1, 1 minus 3. 1, 1. So perpendicular to V1, here is V1, perpendicular to V1 is that. So we are then saying a normal vector perpendicular to the plane V1 is 1, 1 minus 3. Since V2 is perpendicular to V1, okay, we can see that V2 is perpendicular to V1. The vector 1, 1 minus 3 is parallel to V2. Okay, we can see this vector, it is parallel to V2. Okay, that's what this is saying here. Right, so it's parallel to V2. And V2 contains the line L. We know that V2 contains the line L according to the description there. Okay, right. Therefore, the vector 103 is also parallel to V2. Okay, we found the vector 103 in the previous question and formed by these two vectors. And therefore, the vector 103 is a vector that is also parallel. Right, so it's parallel to V2. Then a vector perpendicular to V2 is. So we need a vector perpendicular to V2. And I want us to look at these, but look at these very carefully here and think together. Once again, you have, and I want to use the same sketch here. So if there's V2, V1, and L, there's V2, V1, and then L. Okay, there's, yeah, plane V2, plane V1, and they're perpendicular to each other. And then we have the line L here. Okay. And we have noted that the 1, 1 minus 3, let V1 be the plane defined by this. So if V1 is defined by that, it means that we have a normal to it. A normal to V1 is this one, 1, 1 minus 3. So we can be able to get a normal here. Why? Why do we even are we interested in this? Because to find an equation for the plane, we need a normal always. We need a normal. And obviously we also need a point on the plane. Okay, right. So yeah, we'll refer to the formula. We'll refer to the formula we used last time. So yeah, we have V1, and V1 is a plane, V1, and it has a normal, which is a perpendicular vector to V1, which is 1, 1 minus 3. We need to then find an equation for the plane V2 that contains, to find an equation for V2, we need a couple of things. So here we need, there is a vector. A vector parallel to the line is the vector 1, 0, 3. We remember the vector 1, 0, 3, which is formed by this one minus that. Okay, this vector minus that. So we already know the vector 1, 0, 3. We got in the previous question. It is parallel to the line. So, now this is interesting. So we actually, therefore, are able to see, we therefore have two vectors. The vector 1, 1 minus 3 and the vector 1, 0, 3, which is I, J, K. And then we have 1, 1 minus 3, 1, 0, 3. Okay. Now, these two vectors, a vector on the line parallel to the line, this 1, 0, 3, and this one are in the same direction. So these two vectors are actually parallel to each other. But now they are parallel to the plane. They are parallel to the plane V2. But now if we find a vector cross product of the two vectors, then we'll be able to get a normal to V2. Okay, once again, this is recorded, so yeah, you should not worry much about copying yet, because we shall be cruising. Right, we block first column and first row, and then it's going to be 1 by 3, which is actually 3, and then plus 0. Okay, because it is 1 by 3, then minus this, which is going to be 0, minus j, unit vector j. And you block this, and that is 1 by 3 is 3 plus 3. Okay, because if you block the first row and the second column, you have 1 by 3, which is actually 3 plus this. Okay, plus the unit vector k. Block this first row and this column, and we have 1 by 0, which is 0 minus 1. 0 minus 1. So 3 unit vector I, 6 unit vector j, and you have k. Obviously, this is this one here, because we took two vectors that were parallel to the plane. 1, 0, 3 parallel to plane V2, 1, 1, 3 parallel to plane V2. We have here this one written in terms of the unit vectors, can be written like this, like so. Yes, like so. Okay, and this guy here is the normal. So is the normal to V2. Okay, and thus, okay, once again, yeah, don't worry much about copying. There are lots of questions we're going to do, and everything is recorded. So thus the 3 minus 6 minus 1 is a normal. Is a normal to plane, or to the plane V2. It is a normal to the plane V2. Now, what then do we have here? Well, now the equation. Right, now the equation for the plane. For the plane V2 becomes Okay, we can say that now the equation for the plane is given by, okay, is given by this formula: x, arbitrary vector x, normal, equals point times normal. Okay, and we can use this formula, or we can use this one. Ax minus x1, by minus y1, cz minus z1 equals 0. So yeah, to find the equation of a plane, we can use the top one or the bottom one. Okay, we are spoiled for choice. And we make mention of the fact that this is the case where the normal 3 we got here, 3 minus 6 minus 1, 3 minus 6 minus 1, and choosing point P, right? And you can choose point P, you can choose this one, 1 minus 1 minus 2, 1 minus 1 minus 2, the point, a point on the plane, a point on the plane. At this point, this means what? At this point, this means that we have the following here. We then have that if we use the formula vector x in for the normal point times the normal, we have the x. X is x, y, z. The normal is 3 minus 6 minus 1. Is actually 3 minus 6 minus 1. The point, we chose 1 minus 1 minus 2. Dot the normal, which is 3 minus 6 minus 1. We dot these things, find the dot product, x by 3, 3x, y and minus 6, minus 6y, minus z equals 1 by 3, which is 3, minus 1 by minus 6 is actually a 6, minus 2 and minus 1 is actually a 2, so that we have 3x minus 6y minus z equals, so this is actually equal to 11. And this is the equation of the normal. Right, so is rather the equation for the plane V2. And because that's what that was the question, find an equation for the plane V2. So this one is the equation for, is the equation for the plane V2. Right. For the plane V2, that contains the line L, and is perpendicular to V1. Okay, so this is the answer to question 3x minus 3y, 3x minus 6y minus z equals 11. Okay, just to take note of that. But also this can be written as 3x minus 6y minus z minus 11 equals 0. So the 11 can also be transposed to the left-hand side of the equation, in which case if it becomes 3x minus 6y minus z minus 11 equals 0. Let's look at the next question. Right, next we focus on, once again, these things are being recorded, so you'll have a chance day and night with the video. I'm going to send the end of our discussion. You can watch and replay and whatnot. Determine whether the following limits exist, either by giving a proof from first principles or considering limits along curves. Right, we shall look at this limit here and look at how this is done. So first things first, we focus on the first question. And now to actually determine whether the following limits exist, either by giving a proof from first principles or considering limits along curves. So, but obviously this one is our old friend from Calculus 1. And we note that to do the first question, we say from what you call L'Hopital's rule. From L'Hopital's rule, we know that the limit as z tends to 0 of sine z over z equals 1. Okay, we know from L'Hopital's rule that this is 1. With this in mind, we let z be x plus iy. So you can take this guy and make it the x plus y and make it x plus iy. Now, for every epsilon positive, there exists a delta positive such that if, yes, please.
Sir didn't explain why we jump straight to L'Hopital's rule.
Okay, that's fine. All right, now obviously the reason why we're jumping straight to L'Hopital's rule is because of the nature of the limit. First and foremost, we use L'Hopital rule when the limit itself does not exist. So we're able to see that if you have the limit of sine z over z as z approaches 0, you would have sine 0 over 0. If you take the limit straight away, and what is sine 0, which is 0 over 0? And 0 over 0 is what you call is indeterminate. Right, it's indeterminate. Right, because it is indeterminate, or what you call an indeterminate form. Right, and 0 out of 0 is undefined, indeterminate, and therefore we actually obviously had to use L'Hopital rule to evaluate the limit. Okay, and obviously that is a very popular result in first year calculus, calculus 1. Excuse me. So now, obviously, that's the reason why we use L'Hopital rule there. Okay, but yeah, this once again is recorded, so you'll have the access to this whenever you need this video to see exactly what happened here. Okay, now let us continue to analyze this. Now, we then come to this particular limit and the function of the limit, and we then say, let the x plus y be z. So let z to be x plus y. Now, for every epsilon positive, there exists a delta positive, okay, such that if, okay, this statement is it's a very, very popular statement in calculus, such that if, okay, let me write here. Let's write this one here, such that if 0 is less than the modulus of z, less than delta, then we know that the modulus of this function, right, which is the sine of x plus y divided by x plus y, this minus 1 is less than epsilon. Okay, because we just take this one because we know this limit is 1, and then we can just take this function minus the limit, which is 1, and it's less than epsilon. Now, for every epsilon positive, there exists a delta positive, such that if this is the case, then that is the case. The objective here becomes to find delta that depends on epsilon. Right, so we proceed as follows. And we're able to note then the modulus of x plus y, which is going to emerge in the denominator, is less or equal to the modulus of x, the modulus of y, by the triangle inequality. By the triangle inequality. By the triangle inequality. Okay. Hence, if you have x plus y modulus, it's going to be less or equal to the modulus of x and that of y. And what is this exactly? What is this precisely? We can therefore be in a position to note that at this point, this is less or equal to the modulus of x and that of y. And this is equal to this modulus and this. Okay. Now, note this as a matter of fact. So that the modulus of x is less or equal to the length of x and y. And the modulus of y is less or equal to that as well. So in principle, this is the case here. This becomes the case there. So these are, yeah, I want to sort of explain these because it's very basic, yet obviously students can miss this out. I'm going to do it in green. So, I mean, first and foremost, we know that if you have the length, in mathematics, the modulus of x or the absolute value of x is the square root of x squared. Okay, the square root of x squared is equal to this by definition. Okay, so, but now we can increase the size of the right-hand side. And wherever there is x squared, we can include a y squared. But now if you include a y squared, because the y squared is greater or equal to 0, so the right-hand side is going to be bigger than the left. Now this, therefore, is this. And that is the reason why here, wherever now you think the modulus of x is less or equal to the length of x and y, but also the modulus of y is less or equal to the length of x and y. Okay, so in a nutshell, what we're also effectively saying is if you have the modulus of y, it is actually exactly this. It is the square root of y squared. Okay, this is square root of y squared. But this, we can increase the right-hand side, in which case, therefore, we can put x squared. By Pythagoras theorem, the square root of x squared plus y squared is like the radius. Okay, this is like the radius, because if you have a position vector, you have two coordinates like that. Therefore, this is a y and that's an x. And therefore, now you can be able to find the length, and the length of this is the by Pythagoras theorem. Okay, if you have the length of x and y, it is actually the square root of x squared plus y squared. It is the square root of x squared plus y squared. So that's something that you need to note, that it is actually the square root of x squared plus y squared. Note that. Okay. X squared plus y squared square root is the length of the hypotenuse. This is Pythagoras theorem, and yeah, something we very familiar with. Now let's continue. Let's continue. Okay, if you add this to that, it is twice x and y. It is twice x and y. Right, so now since 0 is less or equal to the length of x and y minus 0, 0, so we're dealing with the bottom of this. So we're taking this xy vector and we are minusing the 0 and 0. So since this here, we can take it to be delta out of 2, because delta out of 2 itself is less than delta. Then 0 is less than x plus y less than delta. Less than delta. Okay. And remember, we're still doing part A. And the modulus of the sine of x plus y divided by x plus y, it was minus 1. It is minus 1. This is less than epsilon. Then we have proved from first principles that we have proved from first principles that the limit as x and y approach 0 and 0 of the sine of x plus y out of x plus y, this limit equals 1. We've proven that this limit equals 1. Right, so since this is less than delta out of 2, then this one is going to be less than delta, because it has both x and y. It has both x and y. So then 0 less than x plus y less than delta. And this absolute value, or the modulus of the sine x plus y over x plus y minus 1 is less than epsilon, then we have proved from first principles that this limit is 1. Okay. Okay, this is there, and think about it. Let's do the next question. Yes, please.
I don't understand why you only dealt with the bottom part and never touched the upper part, like the sine sine open bracket x plus y. Like you only dealt with the lower part.
Yes, we dealt with the bottom part. Yeah, I get your point that it appears as if we dealt mostly with the x plus y. And the reason why we dealt with the x plus y is because simultaneously the sine of x plus y also is a function of x plus y. But moreover, it is because of the fact that our delta itself, delta lies between, or yes, we have that the modulus of z, and z is x plus y. So we have that from the onset of the problem, the absolute value of x plus y lies between 0 and delta. So yeah, we said if 0 is less than the absolute value of z less than delta. So in other words, the z is x plus y. So that now you have that the modulus of x plus y is actually what we need to mostly focus on. And that is what we need to ultimately achieve. Because at this point, we're able to realize that since this, by definition, the vector x and y minus 0, 0 is to be less than delta over 2, ultimately less than delta, then we have that this is less than delta. Okay, and that is because of the onset of the statement. And we said that for every epsilon positive, there exists a delta positive such that a focus on the, because we have the bottom here, a focus on the bottom, on the vector x and y, minus 0 and 0, less than delta, would imply that this is less than epsilon. Okay, think about it. I'm sure that we can always have more time to discuss this proof. Okay, think about it. You can always have more time to discuss this proof. Now, next point. Now, the next one is very, very simple. But now, does it exist? Does it not exist? Well, it does not exist straight away, but yeah, we'll prove that. Determine whether the following limits exist either by giving a proof from first principles. The first one exists because of the L'Hopital rule argument, and because it exists from first year, we proved it using epsilon delta. We gave a proof from first principles, but now this one does not exist. Okay, just looking at it, but we're gonna show now that does not exist. And then we shall use the limits along curves. So we do, to do part B, we let C be the curve. Right, so it is a relevant curve. Be the curve y equals x. And there's D, the curve y equals 2x. Okay, we take two curves here. They're enough. They're enough to help us prove this. So thus, with the limit xy approaches 0 and 0. Okay, we're taking it from here. This is the limit. Okay, now we're gonna take it along curve C, which is this one. But if you take it along curve C, it means that for wherever there is y, you can put x. So that now we have the modulus of x. Y is the modulus of x. Okay, yeah. You can even remove the C here, because at this point, what we have here is x and y. Okay, they actually approach 0 and 0. So that here we have x and x, and then because it's x and x, then you can say, you can consider one x approaches that, and this. So because it's the limit of a constant, then it is the constant of the limit. So it is just 1 there. Next. And we also have the limit. Now we're going to take along curve D, 0 and 0. X, Y. Limit. Okay, this one now, it's, you can put here x, and we called D to be 2x. So wherever there's y, we put 2x. But this approaches 0 and 0. Modulus x, 2x. Okay, right, because it's x approaches 0, 2x approaches 0, it means it's the limit as x approaches 0. Modulus of x, 2x. Okay. So we have 2x here. Okay, yeah. What is this? This is the limit. X approaches 0. Okay, x approaches 0. Okay, modulus of x, modulus of 2, modulus of x. Modulus of x cancels, giving us the limit as x approaches 0 of 1/2. And this is 1/2. Okay, we have one limit is 1. The other limit is 1/2. So because these are different, therefore it means the limit does not exist. Now we go on to say, since the limit as x and y approaches 0 and 0 along curve C of this function, This is not equal to the limit along curve C is not equal to the limit along curve D. Okay, and of the function. Okay, this limit along curve C is not equal to the limit along curve D. The limit does not exist. The limit does not exist. The limit does not exist. Okay, yeah, so this was nice and easy and short because it does not exist. And this is the proof. So determine whether the following exists either by giving a proof from first principles or considering limits along curves. We used limits along curves and we showed that the limit does not exist. I believe that is clear enough. Any question? No question, I believe. Right?
No question.
Okay, thank you. Okay, leave more space. Right, now question 3, it's interesting and very easy. Consider the R2 to R function defined by this. So yeah, we have this R2 to R function given by this. Find the critical points of F in their nature. So yeah, we have a chance to discuss critical points. And to discuss the critical points, we proceed as follows. So we say the domain. Right, the domain. The domain of F has boundary. Right. Right. The domain of F has boundary. And thus, there are critical points. There are critical points where 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 the gradient of the function is 0 and 0. We compute the gradient of the function f. In the spirit of this module, we say d1f. Okay, we can say d1 f of x and y. d2 f of x and y. Okay, yeah, but this kind of notation is also popular, but you can also write this as fx, fy. It's the same thing because the d1 is a derivative with respect to x and d2 is the derivative with respect to y. Okay, now let us, and this must be 0 and 0. The critical points exist where the gradient is 0. Okay, now the gradient. The gradient of fx and y is now the derivative with respect to x of the function. This one with respect to x. So what do we get here? If you have 1/3 x cubed, if you find the derivative of this one, it is going to become x squared. This one with respect to x is y. With respect to x, it's a 1. With respect to x, 0. With respect to x, 0, 0, 0. With respect to y, the derivative, this is the partial derivative. So with respect to y, if y d2, x has derivative 0. Okay, with respect to y, this one is going to be x. With respect to y, 0 derivative, partial derivative, 0 partial derivative. With respect to y, this one is going to be plus y. With respect to y, it's going to be 7. With respect to y, it's going to be 0. And this is 0 and 0. Like so. Okay, let us analyze this. Let us analyze this. Now, what is this? What is the meaning of all this? Okay, the component-wise comparison, by comparison of the components of these two vectors, the first component equals the first, the second equals the second. So this is able to give us two equations. X squared plus y plus 1 equals 0. Right, we're able to have x squared plus y plus 1 equals 0. But which is this one? The second one is x plus y. X plus y plus 7 equals 0. Like this. Okay, now we continue. We perform some algebra, subtracting. Subtracting equation 2 from equation 1 gives. Okay, subtracting these two equations. So subtracting equation 2 from equation 1, you'd have x squared minus x. So the y minus y is 0, and then we have y 1 minus 7 giving us a minus 6. Okay, let us quickly factorize this one. I know it's easy. Factors of x squared are x and x. And then we have minus 3 plus 2. Upon careful examination, we have x equals 3 or x equals minus 2. Okay, this is what we do with the critical points. And so if x equals minus 2, for example, doesn't matter, we can start with x equals 3 because it's on the left here. Doesn't matter. And you can start with any of these. But if x is 3, we substitute into the original equations, these equations. And we want to get y, because these are simultaneous equations from high school. So, for example, if these are simultaneous equations, if x is 3, we can use the simplest one, which is the bottom one here. Right, so we have x plus y plus 7 is 0. X is 3, which is 3 plus y plus 7 equals 0, which means y equals, minus 10. If x is equal to minus 2, we have x plus y plus 7 equals 0. X is minus 2, so we have minus 2. We want to solve for y. These are simultaneous equations. Therefore, we're using elimination to do this one. And then 7 minus 2 is a 5. But bring the 5 across, it makes it negative. So we have those. So, I mean, what is the meaning of this? Well, it means that thus the critical points, are, what are they? There are two of them. Okay, when x is 3, y is minus 10. And when x is minus 2, y is minus 5. Okay. Like so. Okay, now we'll continue. What do we want? Remember, we found the critical points, but now find the critical points of f and their nature. So now we found the critical points. There are two of them, but we must just now describe their nature in terms of their settle points or their minimax points, etc., etc. Okay, now let's continue to investigate the nature of these points, of these 2 points. So now we then say to determine their nature. Their nature we compute. To determine their nature, we compute the determinant. or what you call the discriminant. Right, so we compute the discriminant. We compute the discriminant, and the discriminant D, which is fxx times fyy minus the mixed partial derivative fx and y. Okay, now let us consider the function. So we want to find the nature of the critical points we've already got. Always we use Martinez equations for the critical points. But now, here we want to find fxx. With respect to x, okay, let's find first. It's going to be tricky. Let's find step by step. First, partial derivative with respect to x, fx alone. Bring down 3. It's going to be x squared. With respect to x, it's going to be y. With respect to x is 1. With respect to x, 0. You come to this one, which is 2x. Okay, these are 0 with respect to x. So differentiate for the second time, partial derivative. Okay, now let's come to this same function. We're going to do fy because we need fyy in the discriminant. So first we're going to find the partial derivative with respect to y. This one is 0. With respect to y, it's only x. With respect to y, it's 0. With respect to y, this one is just y. Bring down 2, subtract 1 from the power. With respect to y, it is just 7. And then derivative of this one is 0. But now we find the second one. Differentiate again with respect to y. So it's just going to be 1 because this is 0 and that is 0 with respect to y. Partial differentiation. Now we continue. fxy. Okay, there's fx. Fx is this one. Then differentiate this fx with respect to y. This is fx. Differentiate with respect to y. So this is going to be 0, 0, and this is going to be 1. Therefore, the D, which we've already said is fxx, fyy minus fxy. And fxx is 2x. Fyy is 1. Fxy is 1, which is 2x minus 1. Okay, we found the discriminant now. What is the discriminant? Right, hence the discriminant. Right, the discriminant is D equals 2x minus 1. Okay, we found this one. But I want us to continue and find and evaluate this one at the critical points. Right, we remember the critical points. We found 2 of them. And then now we're just determining their nature. So the critical points we found -2, -5, and the 3, -10. Okay, so now we're going to find a discriminant, evaluate discriminant at 2 minus 5. This one. Okay, x is what? Xy. X is -2, which is -4, -1, -5, negative. So -2 minus 5 is a saddle. It's a saddle point. Okay, it's a saddle point according to the classification because the discriminant is negative. Is -5 at this critical point. Now the discriminant can be evaluated, is to be evaluated now at 3 and -10. Okay, let's substitute here. Okay, it is 2x minus 1. So 2x is 3 x, y. X is 3 minus 1. So this is exactly 6 minus 1, giving us a 5. And this 5 is a positive number. So 3 minus 10 is a local extremum. Is a local extremum. Okay. So being a local extremum, because now it's tricky, this one. If the discriminant is less than 0, then it's a saddle. It's a saddle point. But if it is bigger than 0, then we need to investigate further. Now, we're going to evaluate this one at fxx. Now, okay, what is fxx? Fxx we know is 2x. Okay, so fxx is 2x. We got it before, just the second derivative, twice with respect to x. And then now we're going to find fxx evaluated at this point that is tricky, that is greater than 0, which is not necessarily a saddle point. Okay, 3 minus 10, then we're going to put 2. What is our x here? It's a 3. 6. And 6 is positive. So now, because the fxx is bigger than 0, therefore, right, therefore, or thus, this critical point, 3 minus 10, is a local minimum. Is a local minimum. Yeah, we're finishing. We're pushing. I want to cover much. Okay, it's a local. Right, I want to say it's a local minimum. It's a local minimum. All right, it is a local minimum because the fxx is bigger than 0. As much as also the discriminant is bigger than 0, it becomes a local minimum. Otherwise, it becomes a local maximum. Now, we need to spend a bit more time on the classifications of these, okay? Because there are lots of classifications that we need to learn, and I'm here to spend more time on this section of critical points and their nature in the classifications of critical points. Okay, I want us to discuss the notion of the chain rule for determining the derivative of the function, the composition of f and r, vector r, and vector r is an r to r3 function, and f is an r3 to r function. Okay, this is about statement, so we need to state. That's all. So this is the statement. If vector r is an r to r3 function, that is differentiable. Is an r to r3 function that is differentiable. That is differentiable at t, and f is an r to r3 function. Is an r to r3 function that is differentiable at r of t, then the composition then the composition of f and r is differentiable. It's differentiable at t end. And the composition of the function f with the vector r is the gradient of f r at t r primed at t. Okay. Yeah. Now, if r is an r to R3 function that is differentiable at t, and f is an r to R3 function that is differentiable at f, at r of t. So yeah, with f is a function that is differentiable at r of t, then the composition of the two functions f and r is differentiable at t, and this is the derivative. Okay, this is called the chain rule for determining the derivative of the function, which is a composition of the two functions f and r. Okay, just for 2 marks there, normally this suffices to write in that manner. Next question. It's bookwork. Nothing strange there. Okay, I'd left a bit more space for the chain rule. Okay, let us apply the chain rule to just find derivative of a function. Now, we have been given a multivariable function, a function f of 3 variables x, y, and z. Okay, it is the product of x, y, and z. And the r to R3 function r is defined by this. Use the chain rule that you stated in part A to calculate now the derivative. So yeah, I'll just want to use the chain rule here. Let us use that one. Okay. Let us use that one. But first, to use that, we first find the gradient of the function. So we find the gradient. The gradient of the function x, y, z. Okay. What is this? Is d1f, d2f, d3f. Okay, this is in the notation of this module. d1 is derivative with respect to x of this one. With respect to x, differentiate x is 1, and you're left with y, z. d2, with respect to y, derivative of y is 1, you're left with x and z. d3, with respect to z, derivative of the z alone is 1, you're left with x, y. Okay. And now this is the r, and then by the chain rule, you need to find the derivative of this one with respect to r. So it's going to be okay. But first, let us write the r as it is. Okay, and therefore we want to now compute r primed of t. With respect to t, the derivative of e is e. E to the t is e to the t. The derivative of e to the minus t is e to the minus t, but you multiply by the derivative of the top. The derivative of the top is minus 1, making it minus e to the minus t. The derivative of the t alone, with respect to t, it's like the derivative of x with respect to x. It's a 1. Okay. Now, and let us find the gradient of the function f r of t. Okay, now let's look. This is the gradient, but now we are replacing x, y, and z with this other triple. So this is our x, our y, and our z. Okay, we put them, they must appear here. So what is our x there? Okay, we must put y here and z. Y is e to the minus t, z is t. So this is going to be te to the minus t. X is e to the t, z is t. Te to the t. X is e to the t, y is e to the minus t. You multiply them. You multiply this and that. Multiplying this and that, you just subtract the exponents. The bases are the same. So it's t minus t, the top, e to the 0 gives us a 1. Now that is something you need to note. And this then allows us to say hence. Hence, by the chain rule, we find the derivative of the composition of the two functions, which is the gradient of f r of t, r primed of t. Okay, we've already found the gradient of this f r of t. Okay, gradient of f r of t is t e to the minus t t e to the t 1. And this r primed is what? Which is e to the t minus e to the t. Okay, just the derivative of this one, of the r with respect to t. So this is going to be minus, and the derivative of t alone with respect to t, it's a 1. Okay, component-wise multiplication, this by this times that, it's t. This times that is minus t. Okay, and thus fr. Okay, yeah, so this one is 1. Okay, so this is 1. So yeah, use the chain rule you stated to calculate the derivative of this, or we use the chain rule to find the derivative of these, and we found that the derivative is 1. Okay, just take note of how we use the chain rule here. Once again, I mean, you have a chance. This is recorded, so yeah, you have a chance to watch this replay, and so on. All right, the next thing we are moving to Lagrange. Okay, you must also learn optimization. Right. Optimization. Optimization is a very important part of this module. So it's something you need to understand. Now, a delivery company needs the measurements of a rectangular box such that the length plus twice the width plus the height should not exceed 300 centimeters. Use the method of Lagrange. Okay, the method we're discussing is the method of Lagrange to find the maximum volume of such a box. Let's discuss the method of Lagrange. Okay, remember that we're finding the maximum volume of such a box. And this box is a very exciting box. Boxes, right. Here's the box. X, Y, Z. Okay, yeah. The length, the breadth, the height. So the height of the box is like Z. Okay, something like that. So we will let X be the length, Y be the width, and Z be the height. Okay, and Z be the height. Okay, like so. Now, the volume. Okay, this one is from even high school, primary school. The volume of the box. So normally there's one question that comes. What is the volume of the box? It's a function of 3 variables because it considers volume is area of base by height. Okay, wait a minute. Volume is area of base by height. So it is length by breadth by height. So it is X, Y, Z. Length by width by height. Okay. So it is exactly this one, which is length by width by height. Now there's something called the constraint equation. Right. There's something called the constraint equation. So we always seek to cover the constraint, and that's what the examiner is saying here. They're saying a delivery company needs the measurements of a rectangular box such that the length plus twice the width. So this is what is giving the constraint. So we call it GXYZ. So right, such that the length, right? So if you have the length, and we call the length X, plus twice the width. Okay, the width is Y. Right, so that the length plus twice the width plus the height is Z, should not exceed 300. So it can always be 300 or less. And so we must maximize V volume subject to, we must maximize V volume subject to the constraint. The constraint that G is 300. Right, so obviously, I mean, we need to find the maximum volume of such a box. So we need to maximize, but subject to the constraint that G must be 300 or less, or just 300. We compute. So it can't exceed 300. So we compute. We compute the gradient of the volume. Okay, then we're going to state the method of Lagrange. The gradient of the volume function. Okay, yeah, this is the volume, but we want to find the gradient. So the gradient, we know, we find the derivative with respect to x, and it's 1, it's giving us yz. The derivative with respect to y, this becomes 1, then we're left with xz. The derivative with respect to z is 1, we're left with xy. Okay. So we found the gradient of the volume, but according to the method of Lagrange, you must find the volume of the gradient of the function we need to optimize, which is the volume, but also we must find the gradient of the constraint function, okay, the constraint equation, which is this one. So now we're going to find the gradient of this one. Right, so with respect to x, it is only 1. With respect to y, 2. With respect to z, 1. Okay, so that's what we have. Then for some lambda, then this is the method of Lagrange, the formula for the method of Lagrange. Then for some lambda, right, so we then say the gradient of the volume function. For some lambda, it is equal to lambda times the gradient of the constraint equation. Okay, so this becomes the constraint equation. What is the gradient of the constraint equation? It is x, y, z. Okay, that's what we have. So what is the gradient of the volume function? It is exactly this one. It is yz, xz, xy. It is yz, xz, it is yz, xz, xy. lambda. The gradient of the constraint equation, okay, this thing here, this equation here is the most important. It's everything we need. And this is called the method of Lagrange, this. Okay, now, we then say, what is the gradient of the constraint equation? It is 1 to 1. Put it here. So 1 to 1. Like this. Multiply by distribution. YZ, XY, no. XZ, XY. Okay, so this one is XZ. XZ, and this one is XZ, then it's XY. Okay. Okay, multiply 1 by lambda, 2 lambda by 1, lambda. Okay, now, what is this? Therefore, right, therefore now we can equate everything. So which means that YZ equals lambda, XZ is 2 lambda, XY is lambda. Okay, this. What is all this? Therefore, because this one is lambda and this one is lambda, it means that XY is YZ. XY is YZ. Okay. And so, because there's YY, and so it means X equals Z. Y cancels, which means X equals Z. Using the first, and third, okay, I need to just be careful here. Okay, I need to select the equations that are going to work. Because you've already used the first and the third equations, and we got X equals Z because like Y cancels, if you like. So giving us X equals Z. Right, so let us use also this equation. Because if X equals Z and you put Z here, using the second equation, and now you're gonna, if you put X here, which is Z, so you're gonna have Z squared is 2 lambda. You're gonna have X squared is 2 lambda, or Z squared is 2 lambda. But also here you can use this one because X is Z. So using the second and third equations. Okay. Using the second and third equations. What do we have? Right, so here in the place of Z, you put X, giving us X squared is equal to, and here you put, so yeah, you have X squared, so you replace Z by X. So you also come here in the, or there, in this case, you replace Z by X. So you can put yx. And this will therefore be the same as what? Okay, let's analyze these together. Let's analyze these together. Because this is going to be 2 lambda. Right, it's going to be exactly 2 lambda. And okay, I need to write this carefully. Right, so obviously this is going to be, if x equals z here, you'll have exactly, in the place of z, you put x, so it's going to be x squared equals 2 lambda. Let's just write that one. Right, to avoid mix up. So you have x squared equals 2 lambda. Because x equals z, so and here we replace z by x, getting x squared. So we can replace z by x, getting yx equals lambda. Okay, and this means x squared equals 2 lambda, which is 2 yx. And so what is this? If x squared equals 2yx, right? And so we can manipulate. Okay, it's say 2yx. Okay. Right, so I need to write the property here, 2yx. Okay. Now here you can do anything. Pulling out x, it's x minus 2y equals 0, and this means that x equals 2y. X is not 0, so x is 2y. Since, okay, what is the constraint equation? It is this one. Okay, it is gxyz equals x plus 2y plus z. gxyz is x plus 2y plus z. X plus 2y plus z equals 300. X plus 2y plus z equals 300. Okay, but we already have that x is 2y. Since that we see that, okay, let's see. Because x is 2y, so wherever it is 2y, you can put x, getting wherever there's x, you can put 2y. Okay, wherever there's x, we have 2y. Okay. Okay. Plus z equals 300. What else do we need here? And now let us look at these, but look at this very, very carefully and reason what this means at this point. Okay, and obviously, I mean, what is very evident is that 4y plus z is 300. But what else do we have? You also have that, for instance, we had that x equals z. Right, we also had that x itself equals z. However, look into that, you're able to see that that is not perhaps very, very useful. Right, so we need another constraint to use here. We need most certainly another constraint to put to use. So let us, so now we need to find another relation that is going to make this one variable. Because if it makes this one variable, then we're good. So we need a connection between y and z. Let's go back to the equations. So if we have these two equations, can you get a connection between y and z here? Right? A connection between y and z. For instance, if you look at any of them, maybe this and that. If you divide them to each other with each other, z cancels. Okay, if you look at this and that, if you divide them with each other, so y would cancel and then you'd have z and x. But now if you divide these two, you have y and z. Aha, there it is. So you can okay. We continue. Okay. Okay, yeah. So you're good. Okay, yeah, we're good. Yeah, we're good. Yeah, we are here. Okay, I'm then saying if you look at these two, so you can take xz equals 2 lambda, xy equals lambda. Xz equals 2 lambda and okay, xz equals 2 lambda, xy equals lambda. Okay. Call this equation 1 and call this equation 2. Okay, so if you take these two equations and divide them in the following way, say 1 divided by 2. 1 divided by 2 so that you have xz. You divide by xy is equal to 2 lambda over lambda. What is this? Okay, x is going to cancel out, giving us z over y is equal to 2. You cross multiply here so that z equals 2y. Okay. So yeah, we found one equation. Need to be cunning here a little bit sometimes to just play around with these equations. So we can say, okay, I already called this one 2. So let's call this one, call them 3, 4. Call them 3, 4. Right, so you put 4. Yeah. It's common practice to write the things here. Put equation 4 into 3 into equation 3. Right, so you put equation 4 into equation 3. Okay, so we have 4y plus, what is z? Z is 2y equals 300. 6y equals 300. Okay, if we say 6y is 300, we want to get y. So you divide by 6, both left and right. And then it means y equals, okay. Right, let's divide. 600 divided by that. 300 divided by 6. We have 50. So we get y equals 50. And now okay, we just multiply equations, these things here. So, but z is 2y. Z is 2y, equation 4. And from equation 4, z is 2y, so that is 2y is 50. We want to get x, y, and z, remember. Okay, 2 by 50 is 100. So Z is 100. And then now it remains to get X as well. It remains to get X as well. And so using, just check to get one of the equations. You can get anyone, but any equation that has X in it, okay? Any equation that has X in it. Okay, like this one, X is 2y, X is 2y. Okay, so we're gonna use that one. Using X is 2y, you have 2y is 50 and 2 by 50 is 100. Okay. And hence, we have that X is 100. We got the dimensions. Y is 50. Z is 100. Okay, you got that. X is 100. Y is 50. Z is 100. Therefore, the maximum value. Oh, okay. Therefore, the maximum volume is V. Okay, so it is X, Y, Z. X, Y, Z. So this maximum volume is going to be found by saying V. What is X? X is 100. What is Y? Y is 50. Z is 100. So you multiply everything here. 100 for X, Y is 50, which is in the middle, and then Z is 100. So that what we have here is 500,000 cubic centimeters. Okay, so the 500,000 cubic centimeters. Okay, because this one is 500,000. The centimeter is times 10 to the minus 2 meters cubed. So it's going to be 500,000 centimeters divided by 100. So, but you cube it, it's going to be 10 to the 6th power cubic meters. So divide by a million. Okay, divide 500,000 by a million is 1/2 cubic meters. Okay, you can write it as that 0.5 cubic meters. Ah. Right, so let's continue. Now, you must also be in a position to do integration. Now, so far we've been looking at differentiation, but I want us to also look at paraboloids and integration. Question 6 is actually very interesting. Consider D to be the region below the paraboloid. So you have a paraboloid. We spoke about a paraboloid, and there's something called a cylinder, and we shall sketch these things. And there's a plane Z equals 1. Make sketch of D and sketch the intersection of D with the XZ plane for 5 marks. Let's sketch. Right, we've made enough space available for us to do sketching. Let us sketch a little bit here in question 6.1. And then, okay, these are too many questions I planned today. So yeah, it's but yeah, we're gonna do the most we can. But now I want us to look at the fact that now we want to sketch in a Roman figure 1, we have Z. 3 plus. Okay, and then, okay, we're taking this one. So Z is this one. end. This is the case. Okay. Here you can write z minus 3 is x squared plus y squared. Okay, we transpose the minus 3 to the other side, and we have like x squared plus y squared there. But we do not forget that the x squared plus y squared itself is 1, so that we can substitute it here and have z minus 3 equals 1. Right, and this means z equals 4. Okay, take note of that. Now, if z equals 4, what does this mean? Right, so, well, I mean, we are looking at by substituting one equation to the other, we are looking at the intersection of our paraboloid together with the cylinder. So at the point at which the paraboloid, like a parabola in 3 dimensions, meets a cylinder, they meet at a circle. A cylinder is like a drum that is open at each end, and therefore, if this paraboloid is open, this cylinder is going to cut this into a circular cross section. Okay, now, right. So we analyze what that means. So at the point at which we have this, so it means therefore you'd have the following sketch. Right, so you have the following sketch. Z, Y, and X. Okay. Then there is a drum. Right, so this cylinder, this one, is, if you're here, on the XY plane, it is a circle centered at the origin of radius 1. But then obviously you can look at it here, minus 1, 1, minus 1 here. But now it's going to cut at z equals 1. And then there's z equals 1, and then there's also z equals 4. Okay. 1, 4. And this is the case. We have that. And then this one is 3. So we have this. Okay. So let us analyze this. Okay, this is going to be at 1 here. This is going to be at a 4 here. And this is going to be like 3 in the middle. Okay. Remember that inside the cylinder, so when we're consider D to be the region below the paraboloid. The paraboloid is going to cut at 4. Z equals 4. So below the paraboloid, inside the cylinder, above the plane Z equals 1. So the Z equals 1, but it's above. So you have between 4 and 1. Between Z equals 1 and Z equals 4, you have that part of the cylinder, because this cylinder, this drum goes to infinity, goes up and goes down. So, but yeah, we're just interested in it between Z equals 1 and Z equals 4. Okay, let's see what we have here. Okay, so make a sketch of D, because D is the region we want, and sketch the intersection of D with the XZ plane. So the intersection with the XZ plane. So the XZ plane, if you are to slice these according to, this is the X and then Z, you slice it. So it's going to become this. It's going to become exactly this, -1, 1. And then it's going to be like a vest. The paraboloid is going to make it have that kind of shape. So this paraboloid, at the point that X is 0, Y is 0 on the Z-axis, you have 3 plus 0 squared plus 0 squared, which is only 3. So it's going to cut at 3 here. And this one is at 4 here. So in the end, then, right, so, okay. So this is the sort of cross section. So if you slice it, then this is going to be, it is the cross section of the XZ plane. So this is ZX plane, like that. This one is going down. Okay. So yeah, this becomes the answer. So this one becomes the XZ plane. XZ plane. Okay, so we have exactly that. Um, right, we continue. Okay, right.
Yes.
Yeah, okay, yeah, we're done with this. Okay, we're just talking to another student. Okay, yeah, sorry, this is exactly what we sort of have. It's the idea of what's happening here. But just take note of the sketch, because sketching is part of what you need. Sketching in 3 dimensions is very important. Okay, express the volume of D in terms of a triple integral using the cylindrical coordinates to not evaluate the integral. Let's look at the second Roman figure. So we need to express now the volume of D in terms of triple integral using what we call cylindrical coordinates. Cylindrical coordinates are the X, Y, Z, and with R and theta, Right, so you confirm, you transfer, you change the X, Y, Z to R theta Z. Okay. 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 All right. Okay. Now, let us express this in terms of the now I want to say first the volume. The volume of D in terms of triple integral using cylindrical coordinates. Okay, so the volume of D using cylindrical coordinates, we've already seen, therefore, that at this point, the radius is mostly, for instance, here in the XY plane from 0 to 1. So R is from 0 to 1. This thing here is the circle. The cross-sectional view is circular. It has some circles at each end of this cylinder. Okay, but we're looking at it from Z equals 1 to Z equals 4. Okay, now then because it's a circle, a full circle in mathematics is a full revolution. So theta is from 0 to 2 pi. 2 pi is like 360 degrees. That's a full revolution for a circle. Cross-sectional view at each end of the cylinder. Okay, now there's something called the paraboloid. This one. This paraboloid now is between 1, z equals 1, z equals 4. We saw that. Okay, but simultaneously, there are things you need to remember that x squared plus y squared in the cylindrical coordinate system is r squared. 1 less than z less or equal to x squared plus y squared. Okay, x squared plus y squared plus 3. And this is actually now the x squared plus y squared. We said that x squared plus y squared is r squared. So we can put r squared plus 3. Okay. So which means therefore now z is bigger than 1 because we're looking at that we're able to then say now the volume of D. Okay. The volume of D is equal to the triple integral 0 to twice pi, 0 to 1. You'll understand this, please, now. I'm just writing these things here, and then we shall elaborate on them. Right, so 0 to 1, and then 1 to r squared plus 3. And if we want to find the volume of D, we put 1, the number 1. R dz, dr d theta. Theta being the angle, 0 to 2 pi for a full circle, 0 pi over 2 pi, 3 pi over 2, then 2 pi radians. So if you go anti-clockwise like this, we actually have a full circle there for a cylinder. So the theta, which is on the outside here, runs from 0 to 2 pi. Okay, now the radius. The radius of the circle x squared plus y squared, this is like a circle in 2 dimensions. Okay, in school we say it's a circle, but it's just that now when you go to 3 dimensions, we see that it becomes a circle when you're on the xy plane. But now these things are extended upwards and they become vertical lines. These vertical lines trace a drum, which is formed by too many circles like this. And these circles now form what we call a cylinder. And then in the end, the radius is therefore the radius of 1, which is this is x squared plus y squared. X squared plus y squared is r squared, and the radius is 1. Okay, from high school. And then now the z. We've already seen that z is going to start from 1. Z is going to start from 1 because z is 1. This is between z1 and 4. Z is 1 here. But now, if you draw an arrow like this, z then becomes z equals 3 plus r squared. The x squared and y squared, they become r squared because we use Pythagoras. So we move from z equals 1 to z equals 3 plus r squared. Because the paraboloid now, an arrow that is going to penetrate the region, is going to meet this region at a section of the paraboloid, which is a parabola in 3 dimensions. But the parabola with x squared plus y squared equals r squared means z is equal to 3 plus r squared. Okay, that's the thing. So, so that is why this is going to start from the z in the cylindrical coordinate system. We're going to discuss these coordinate systems in detail, but we're starting from 1 to any part of the paraboloid, looking at the xz plane, right? So, and this here is z is z equals is z equal to paraboloid? Is z equals to the x squared plus y squared plus x squared, however, x squared plus y squared is r squared there. Okay, and this we don't need to evaluate. So it is actually the answer. Do not evaluate the integral, just find it. Express the volume D in terms of the triple integral using cylindrical coordinates, which is the r theta z coordinate system. The r theta z coordinate system is what we call the cylindrical coordinate system. All right, yeah, we've discussed much for today. There are too many things I would like us to do, but on average, we've averaged our time so well. We've covered nearly 2 hours by just a minute. Just that I timed myself, but sometimes this thing does not show me the time. But it's about 2 hours now. Okay, I have a lot still to do. I can talk the whole night. but time becomes the limiting factor. In our next appearance, we'll continue with more things that you need to do. And I'm going to give you more information about the things that we need to do. Okay, right. So any question now?
My request would be that next time when
Yes,
we have a class, please let me know the topics that we are going to discuss.
in advance.
And
Yeah.
there are 3 topics that I do need like more practice or like more teaching on.
Yes. Okay.
Like the proof of limit, it was you were too quick.
Yeah, I understand. I understand. Okay, I'm going to notify you of the topics we're going to discuss so that you can, let me know if it's ideal or we need to make changes or we need to focus on certain sections and not others, things like that.